Hi, I'm Kathy Levinger. In this lesson, we're going to continue our discussion of functions by talking about linear functions and function notation. Let's start with a discussion of linear functions. For a function to be linear, equal steps in the independent variable must always produce equal steps in the independent variable. It's important to note right here we're talking about functions, so the rules for a function apply, but we want to categorize a specific kind of function to be linear in the way described. Well, let's try out that description with a couple of examples. What we want to determine is if the table below represents a linear function, and what we see is R, an input. Remember, the top row of the table is an independent variable, and T, an output. Our inputs are 6, 8, 10, 12, 14, and 16. Outputs -3, -5, -7, -9, -11, and -13. For this to be a linear function, we need to see if there are equal steps in the independent variable values. I see that to get from 6 to 8, I can add 2. From 8 to 10, add 2. From 10 to 12, add 2. And so on. So there are equal steps in the independent variable values. Now, do those equal steps produce equal steps in the dependent variable values? Well, let's see. To get from -3 to -5, I subtract 2. To get from -5 to -7, I subtract 2. Between here, there is a -2, and another -2, and another -2. So this is a linear function according to our description. Let's try another. Again, we want to determine if a table represents a linear function. So we're looking at the top row of the table being independent variable values, and we want to see if there are equal steps between them, and then we can determine if that is true, whether there are equal steps between the values in the dependent variables. Well, let's see. To get from 7 to 3, I subtract 4. From 3 to -1, I subtract 4, and so forth. So there are equal steps in the independent variable values. Well, let's see what happens for the dependent variables. To get from 3 to 4, I add 1. And from 4 to 5, I add 1. So it looks like I'm going to have equal steps. But the next step is from 5 to 4. And in that case, I would have to subtract 1. That means automatically that this is not a linear function. It is a function, however, just not this special category of linear function. Well, let's continue with our discussion of linear functions and look at a special notation for functions. What we see here is we're supposed to evaluate the function for the given values of the independent variable. But let's talk about this notation for a minute. This is read f of x equals 6x plus 2. F of x is the name of the function. Actually, f is the name. The x indicates that this function named f operates on the variable x. And that means that this x here is a variable in the expression 6x plus 2. F of x is using a function notation to name a function. Well, in this particular example, we're supposed to find 3 function values. Let's start by finding f of 3. What we're supposed to do with the 3 is what's exactly done to the x in the function. F operates on x and does this. So if f operates on 3, it's going to take 6 times that 3 plus 2. The 3 has replaced x in the function. This simplifies to 18 plus 2, which is 20. And so we conclude that f of 3 is 20. Let's find f of -2. F of -2 is found by taking 6 times -2 plus 2. f operates on -2 and does to -2 what f is doing to x in the statement of the function. Simplifying this is 6 times -2, which is -12, plus another 2, which is -10. And so we conclude f of -2 is -10. Finally, we want to find f of 0. We do to 0 what is being done to x in the statement of the function. So 6 times 0 plus 2 is what we want to find. 6 times 0 is 0. 0 plus 2 is 2. And so f of 0 is 2 is what we conclude using function notation. Well, let's continue using function notation in this way. For the linear function given below, we're going to make a table of at least 4 values and sketch a graph of the linear function. Our linear function is f of x equals -2x minus 5. To make a table of at least 4 values, we're going to pick 4 arbitrary values of x. You can use whatever you want. It's usually a good idea to use at least one negative. Let's use -1. And 0 is always a nice convenient value to use. Other than that, I'll pick 2 other x values. To fill out my table, I first find f of -1, which according to the function is -2 times -1 minus 5, or 2 minus 5, which is -3. So f of -1 is -3. Now I'm going to find f of 0. According to my function, that's -2 times 0 minus 5, or 0 minus 5, which is -5. So f of 0 is -5. Now I want to find f of 1. According to my function, that's -2 times 1 minus 5, or -2 minus 5, which is -7. I can fill that in the table. And finally, I want to find f of 2, which is -2 times 2 minus 5, or -4 minus 5, which is -9. I'll fill that in the table. So we found a table, or we made a table actually, of 4 values. We want to sketch a graph. What we're going to need to do is use another piece of paper, and let's translate our table to that, and then we can sketch a graph. -1, 0, 1, 2, -3, -5, -7, -9. Okay, now we're ready to sketch a graph. We need to draw a coordinate system. The horizontal axis is the x-axis. The vertical axis is the f of x axis. You know that this is also the y-axis, and so we're plotting a set of points in an x, y, or rectangular coordinate system. We want to plot the point -1, -3, then 0, -5. That's 0 in the x direction, -5 in the y direction. We want to plot 1, -7, and 2, -9. We connect those points with a line to get a graph of the linear function. Let's look at one more example. For the function given below, write an equation using function notation. Identify what the independent and dependent variables represent. So what we see is Corey uses 6 nails per fence slat. The total number of nails he uses is a function of the number of slats in the fence. What we might do is identify the independent and dependent variables first before we start to write down our function notation. The total number of nails is a function of the number of slats in the fence. So our independent variable value should be the slats, the number of slats. We should call that some variable name. Let's call it n for number. The dependent variable value is going to be the total number of nails. I'm going to abbreviate. Let's use a T for that, for total. And now we want to use the fact that, or work into our function, the bit of information that he uses 6 nails per slat, and write a function. So the total number of nails, T is a function of the number of nails, is equal to 6 nails per slat times the number of slats. And I can simplify that just a little and write T of n equals 6n. And this is one particular function notation that might describe this function. Well, in this section we've looked at functions and function notation. Be sure to work some exercises from your textbook to practice.